Tides at the flood, swirling currents, Father Neptune at odds with himself. These, since time immemorial, have been one of nature's strongest barriers to stay man's march toward progress. How to flaunt water's angry moods has been man's problem since the beginning of time, but progress was slow, limited by materials and engineering imagination. Then, a century ago, came an idea which gave wings to man, to bridge longer, deeper waters. Today, this basic idea, the application of the bridge principle, makes possible one of man's greatest achievements, the longest bridge span yet attempted to conquer that world-famous entrance to San Francisco Harbor, the Golden Gate. What memories this name calls to mind. From it went the clippers in the China trade. To it returned the commerce of the Orient. Through this gate sailed the 49ers seeking gold, and through the Golden Gate was developed a promised land, the Golden West. Today, San Francisco has become a great metropolis worthy of the world's greatest bridge. With the highest towers and the longest main span man has yet attempted. Though San Francisco is teeming with people, just a mile across the treacherous tidal current of the Golden Gate lies Marin County with a paradise beyond it, the great Redwood Empire. Yet across the waters of the bay, now linked with San Francisco by the already famous Bay Bridge, Oakland is crowded with homes. So the bridge across the forbidding water of the Golden Gate must be built. But like Rome, this bridge was not built in a day. In fact, though started in January 1933 and completed in the amazing time of 53 months, this great bridge has really been building for more than 100 years. For just a century ago, when San Francisco was but a few shacks on a rugged hillside, John A. Roebling, then a young engineer, took out his license to practice engineering and was trying to make rope out of wire in a wheat field behind this Pennsylvania home. Working also in this experimental shop, he was laughed at like others in the fraternity of pioneers until his wire rope amazed the skeptics by hauling the bolts of the Pennsylvania Canal up the Portage Railway over the Allegheny Mountains. This success portended the young engineer's destiny. With wire rope and cable, he now had a great new engineering material. He quickly adapted his new material to the suspension bridge principle in building aqueducts, such as this one. He erected the first of these at Pittsburgh in 1844. Wire rope vehicular bridge over the Monongahela at Pittsburgh. But even before the Civil War, Roebling was to startle the world. Here was a man who dared to move a fully loaded train and its iron horse over the gorge of the Niagara River. Other suspension bridges rapidly followed the Niagara, the Pittsburgh Allegheny in 1860, then the Cincinnati Covington. During all the activity, Roebling was on the plans of the bridge that was to be his monument, even though it was to cost his life, the Brooklyn Bridge. Just to see this old print with the thousands of sails on the river makes us realize the courage of a man who dared to plan a suspension span 1,600 feet long and wide enough to serve the traffic of two great cities. Here surely was a feat to stir the imagination of the people of that time and the admiration of generations to come. In 1869, after the plans of the bridge were perfected, accepted, and approved, Roebling received an injury on the work that was to result in his death. He left his son, Colonel Washington A. Roebling, to carry on, to complete the bridge, and to inherit a tradition of engineering preeminence hardly equaled in any other field. Small wonder is it then that the world honored John A. Roebling for his achievements. His statue in Trenton, his home community, serves as an inspiration for generations to come. With the cables of the Manhattan and Williamsburg bridges also spanning the East River, his son Washington and his grandsons have spread the fame of the Roebling name. Then followed two bridges over the lower Hudson, the Bear Mountain, and then the first bridge to connect New York City to New Jersey, the great George Washington Bridge. Less spectacular than his bridges, but equally important, was the factory organization that John A. Roebling had founded to keep pace with his bridge pioneering. As the bridges were built, so the factories grew. Until today, the Roebling organization is made up of 4 great plants in and near Trenton, New Jersey. Under its own roof, Roebling controls every step of the process from the raw material to the finished product. Several thousand men fabricate wire and wire rope from the thickness of a hair to over 4 inches in diameter. Woven wire fabrics, from the finest screening to the heaviest industrial mesh. Welding wires of many grades and sizes. Insulated wire of all standard and many special coverings. So small it can be used in the finest instruments. So large, it carries power to light entire communities. Special carbon and alloy steel flat wires in a wide range of sizes and heat treatments. And finally, in 2 individually housed laboratories devoted exclusively to pure science, metallurgists and engineers have developed wire testing apparatus found nowhere else in the world. Only with such manufacturing and research facilities is it possible to work out the unique materials and the engineering methods by which the Golden Gate Bridge cables were spun in record time. Now let us study the suspension bridge principle. Main towers are firmly embedded to hold their tremendous loads. Hung over these towers and anchored at each end are the main cables. Then, unlike other bridges, the great weight of the roadway and the traffic it will bear is suspended from these cables. How this principle is adapted to the Golden Gate Bridge is shown in a cross-section view looking toward the Pacific Ocean, highly compressed here to fit such a long bridge into the picture. Note that the south tower is on the side where the city of San Francisco lies, and the north tower is close to the shore of Marin County. The strong tides of this Golden Gate have worn the channel down to 318 feet near the center. Above the water, the bridge allows 236 feet of clearance, high enough for any liners or Uncle Sam's battleships to pass under. This clearance height is accomplished with towers 746 feet above the water. This tower height also makes the great length of the main span possible, 4,200 feet, the longest ever attempted. Unlike the George Washington and many other suspension bridges, one of the towers, the south, was placed 1,100 feet from the south shore in 70 feet of water. Because it is placed so far out in the treacherous Golden Gate, the south pier must be protected by a heavy concrete fender wall, strong enough to withstand a collision with the greatest ocean liners and the constant tug of war with the tides of the largest landlocked harbor in the world. 4 times a day, the water of a harbor covering 450 square miles races in and out of the narrow gates, smashing at these foundations. But slowly and surely, steel and concrete build this sturdy island right in the Golden Gate. In the meantime, the north pier is completed and huge derricks begin to raise the steel tower toward the sky. The south tower builds up rapidly too, as the Bethlehem Steel Company erects the great steel members and rivets them fast. Many rivets are needed. In fact, someone figured out that if all the rivets used on these towers and on the roadways were placed end to end, they'd reach a distance of 32 miles. The San Francisco Tower is taking form as the Marin Tower is completed. Time after time, the great derricks, rigged with Roebling blue center wire rope, place the steel sections as far up as they can reach. Then, with a foothold on the steel which they have erected, the derricks literally pull themselves up by their bootstraps. Thus, the tower continues to grow, getting nearer and nearer to the point on which will rest the great cables. When finished, each tower will contain 21,500 tons of steel. That's enough to fully load a freight train almost 10 miles in length. Near the top, another large section is swung into place. When the top is reached, the towers will be 746 feet above the water, 111 feet higher than those of the next longest suspension bridge, the George Washington at New York. 150-ton saddles hoisted to the top of each tower in 3 sections will seat the cables and hold them in place. To accommodate the stretch in the side spans, these saddles move on rollers. If you were going up in that man hoist, you'd realize what it means to be a bridgeman. And if you were not too sick to look around, you'd see San Francisco to the south of you, with the famous Presidio in the foreground. When you're up that high, you're sometimes above the clouds and see only the tops of the mountains to the north. On the shore behind each tower, you'd find the huge concrete mast to which the ends of the cables will be fastened. Since there's no giant strong enough to take the finished cables and hang them right over the tower tops, man has to depend on something greater than any giant could ever be: his own ingenuity. Man spins the great cables out of thousands of small wires laid parallel. But before he can do that, he must build a preliminary bridge on which he can do his spinning. First one rope, then several, and finally a series on which he can support this temporary bridge from one anchorage to another over both tower tops. This temporary bridge is called a footbridge, or sometimes a catwalk. Here the end of the strand has reached the tower top. The footbridge strands are anchored in concrete. Long bolts permit adjustments for proper tension. Hanging footbridge strands similar to these between the towers across the Golden Gate require the help of the Coast Guard and a system of shortwave radio communication to regulate gate shipping as a barge ferried the footbridge strands across from one tower to the other. Let's listen in as the Coast Guard boat patrols its course to clear the way for the barge on its first trip across, and the operator at South Tower calls the boat.
Hello, Coast Guard. Hello, Coast Guard. South Tower talking. Are we all clear? All clear. Go ahead. And you, man tower, are you clear? Can the barge start across now?
Hello, South Tower. We're all set here.
Are you ready, barge? Ready here. All clear. Go ahead, barge. Okay, we're coming across. We're riding fast, reeling out fast. Current's pretty heavy today, so we're heading up a bit. Here comes the halfway connection. Now we're all clear to the South Tower side.
And so the supporting cables, one by one, are laid on the channel bottom for the preliminary bridge and then hoisted separately to the tower tops. Here the last strand is finally up to the tower top to be fastened to the end of an adjusting rod. This permits a perfect fit. All footbridge strands, both in the main span and side spans, are in place, and we're ready to construct the footbridge. The first steel to be hung from these temporary strands is the large cross bridge to be located midway between the towers, known as midspan. This cross bridge, hoisted to the top of Marin Tower, is slung from work cars, which in turn roll it out on the strands to midspan. Oh, there, the work carriage is stuck, and these two bridgemen volunteered to take a little trip out along the footbridge cables. Bridgemen call it swimming the cables. Swim, fellers, or you'll swim the gate, hundreds of feet below. Did they make it? Well, here they are. Meet Muggs Anderson and Clyde Hepworth, the first men to cross the Golden Gate Bridge. Platforms on which the bridgemen will work to spin the cables are now placed to form our temporary bridge. These are slid down to position in groups. This woven wire mesh, another Roebling product, was found strong enough to hold the weight of men and equipment without excess weight. You may have realized by now that balance makes the suspension bridge possible. Balance of the loads on either side of the towers. To maintain this equilibrium, all work proceeds from the towers, out both ways. Thus, as the platforms are placed toward the center of the bridge, others are being hoisted up the sides of the bridge. Let's take a ride down on the work carriage and see how it feels to be a bridgeman out in the middle of the Golden Gate. There goes the tower top. No chance to turn back now. The bridgeman works as if he were on his own back porch. But we've had enough for one day and are ready to go back as the erection of the footbridge continues. When about 3,000 sections are in place, we will have a continuous bridge known as the catwalk. This shows the course the main cables will take. If we cut a section from one of the main cables, here's how it would look. 3 feet in diameter and made up of more than 27,000 small wires laid parallel. Placing these wires from shore to shore is called spinning the main cable. The wires are spun in separate groups of 452 wires each, called strands. Then these many strands are squeezed tightly together, forming the final circular shape of the finished cable. This laboratory cross-section shows how the individual strands have lost their circular form as the compacting pressure has formed them into a solid mass of wires. Though Roebling annually sells millions of feet of steel wire products, bridge wire has characteristics and requirements all its own. Before leaving the plant, each coil of Golden Gate bridge wire is tested for strength and elongation. A carefully calibrated scale tells us that this wire has a tensile or breaking strength of over 235,000 pounds per square inch. This cold-drawn wire made from acid open-hearth steel is the strongest structural material available to the bridge engineer. Because speed in spinning the main cables is so definitely a Roebling creed, these coils must be joined with much longer lengths to eliminate splicing delays on the bridge. So they are shipped by boat to a special reeling plant at California City near the bridge site. By means of the Roebling bridge wire splice, the coils are joined up into large reels containing 30 miles of continuous wire. Engineers say that in a bridge cable, the wire is as strong as its weakest splice. Unlike other splices, the special Roebling splice removes no metal from the wire at the splice point. Grooves are pressed into the ends by a hydraulic press. Over this fits the threadless sleeve or nipple. Thus, no metal is lost. Another press closes this nipple on the ends to be joined and fills in these grooves to seal the bond. Notice that in a test, the wire will break, but the splice will not. After the protective coating of wax is removed, the wire is reeled to its 30-mile length in 2 successive stages and is ready to be shipped to the bridge site. In spinning the main cables, the large reels of wire are unreeled by means of this spinning wheel or carriage, which carries a loop of the wire from the anchorage over both towers to the other shore or anchorage. Then a different loop from another large reel is placed on the spinning carriage and it makes the return journey. Let us examine this operation in an animated drawing with towers and footwalks removed for the sake of simplicity. Here is the strand shoe we saw in the animated drawing. Now, the spinning carriage comes into the anchorage. The wire loops it has carried all the way across from the opposite anchorage are taken off the wheels and looped around the strand shoe. Then, 2 more loops of wire are placed on the carriage. Off it goes for the return trip, moving up the side span to the tower top. As the wires pass over the tower top, they are placed in temporary saddles until a group of 452 wires form a single strand of the great cable. Let's go back to the building of the George Washington Bridge at New York and notice the great improvement 6 years has wrought in spinning technique. There, only 1 wire loop was carried on each trip. On the Golden Gate Bridge, this rate had been doubled, but Roebling engineers were not satisfied with twice the capacity. They wanted 6 times as much, and they achieved it on the Golden Gate Bridge with 2 developments never tried before in suspension bridge history. As soon as the bridgemen had become familiar with handling 2 loops of wire, the rate of spinning was then accelerated 50% by the introduction of a new type of spinning carriage, which now carried 3 loops on each trip. Secondly, the wires were transferred at midspan. Thus, no spinning carriage had to travel more than halfway across, and the wire spinning capacity was doubled. These 2 Roebling developments have made it possible to open this bridge to the public in record time. At midspan, the wires were quickly transferred, and the carriages are now off on the return trip with a new set of wires. At the tower top, the bridgemen reach for the wire and place it loosely in specially designed clamps or vices. A little way down on the walk, a bridgeman attaches a hauling clamp or come-along to the wire. And 2,100 feet away at midspan, the wire adjuster operates the come-along by means of a push-button control. He raises each wire until it is clear of all obstruction, then lowers it to its position in the partially completed strand. When the adjuster is satisfied that the wire is in its proper place, he gives a signal to the tower top, and the bridgemen tighten the clamps on the wire. When the wire from one reel is exhausted, the spinning carriage must stop long enough to replace the reel with a fresh one. The splice is identical with that made in the reeling plant. To control and guide the many spinning operations, a system of telephone and push-button lights connects many points along the line with the dispatcher's office in the middle of the bridge. Practically all sizes and types of electric cable required were selected from the large Roebling stock. Let's listen in as the main span dispatcher hears from the North Tower top spinning boss late one afternoon in May.
If South Anchorage promised you 2 more trips by quitting time, we'll top it, but clear 'em fast.
And the dispatcher did clear him fast, for more than 1,000 miles were spun by quitting time. 1,000 miles in 8 working hours, a record for all time recorded on this Celsin dial. Spinning conditions were not always as calm as we have seen. In fact, when gales blew in from the full reaches of the Pacific, they were worse than any Roebling engineers had ever encountered in their long experience of bridge building. But the bridgemen were never the first to quit. When the needle in this anemometer showed wind velocities over 40 or 45 miles per hour, the bridgemen seemed to delight in fighting the gales. Older and wiser heads among the engineers had to call them down off the footbridges. And despite the many gales, the Golden Gate main cables are rapidly spun. As spinning crews compete with each other, as sharp eyes follow the course of the spinning carriages, and men and machines hurry to the task. Brooklyn Bridge, which amazed your grandfather in his youth, could fit in its entirety, anchorages and all, right under the main span of the Golden Gate Bridge. The next step is to place the suspenders over these castings. The suspenders arrive at the bridge, having been cut to exact length and socketed at the Roebling mills. After hoisting the reels to the tower top, they are trolleyed out to their position, as were the cable bands. Over sheaves which are set on the cable band, they are slowly allowed to drop until the loop is guided into its supporting groove or saddle. Special clamps hold the ropes together below the cable. As we view these suspender ropes which will carry the load of the roadway and its traffic, we may not realize how much one branch of engineering is dependent upon another. Consider, for instance, that not more than 4 of these suspenders have the same length, varying from 23 feet at midspan to 489 feet at the tower tops. Cut to length 3,000 miles from their final resting place, each and every suspender end or socket must come to rest at exactly the correct position. Moreover, it must stay that way through generations of exacting service. Rain, fog, roaring nor'westers, and the pounding of heavy holiday traffic loads. And it will stay that way because so many industries and years have contributed to the science of wire rope manufacture. Wire rope in elevators moving over pulleys and sheaves hundreds of thousands of times a year has produced inexhaustible data on wire rope flexibility. Building industry derricks with their heavier and varying loads have written another important chapter on flexibility. Still heavier loads are served by this derrick of derricks, lifting a fully loaded freight car smoothly and easily. Or contrast the specialized use in this coal loader. Next, wire rope must resist repeated stress in bending, in resilience and tension. Mine hoists carrying heavy loads of ore up and down day and night tell quickly how well the wire rope resists the strains of repeated bending. Likewise do skip hoists for steel blast furnaces. Then there's resilience and tension factors in repeated stress of oil well drilling. Yanking this rope millions of times before it's worn out. Wire rope must be able to resist shock or impact in serving the construction industries. Digging a rock out of the earth may put a stress on the wire rope many times greater than that of lifting it. Excavating the foundation of a building is like digging into an attic trunk. You never quite know what you'll find, but the wire rope on the shovel must be ready for any kind of a shock. And to a lesser degree, the wire rope on this road building machine must be able to take it. And abrasion. The wire rope that's pulling us up out of this mine has been scraping along the bottom all the way up. On the surface, this mine's incline railway gives its wire ropes more hard knocks as it drags its way up the side of a mountain, over pulley, through grit, across wood ties, and over steel switches. The wire rope must resist abrasion. In the thousands of miles of wire rope Roebling has made for the logging industry all over the world, Roebling engineers have garnered data to show them how to fabricate wire rope so that it resists crushing, as these logs smash the rope against rocks on the ground, against tree stumps, against other logs, again and again in tropic heat or frozen north. And finally, wire rope must resist corrosion, whether it be salt or fresh water, clean or sewage muck. When you've learned how to make wire rope that will take the kind and types of punishment you've seen, you're well along the way to making the wire rope that's safe enough for the Golden Gate Bridge. But you're not quite there until you've specially prepared each 3,600-foot length. Whatever non-elastic and unpredictable stretch exists in the rope must first be removed by a process known as pre-stressing. Another Roebling development for accuracy and safety. The rope is run out as a loop along an 1,800-foot track. By means of a large hydraulic testing machine, the rope is pulled or stressed far above any load it will ever receive in service, and held there long enough to remove all of the unpredictable stretch. Now the stretch can be accurately predicted, and the rope will be perfectly elastic. Then tension is reduced to the dead load tension to which it will be subjected on the Golden Gate Bridge. The lengths are now ready to be measured, marked, and then cut on a large shear. For socketing, the ends of the wire are spread out. Next, dipped in a bath of acid to remove the galvanizing and thus clean them. Then the socket is placed over the wires. The servicing or winding will be removed, and the wires again opened, spread out like the ends of a broom. Finally, molten zinc is poured in to complete the seal. At the Roebling Physical Testing Laboratory at Trenton, the final precaution is taken. Samples of the suspender rope are tested in a 2.5 million pound mechanical testing machine to make certain that these suspender ropes meet the high specifications required. After the elastic behavior of the samples are studied, the load goes up and up. Up and up, and with the report of a cannon, the rope breaks. Then again, 2 parts of a rope this time. Up and up the tension goes. As rapidly as the suspenders are hung from the main cables, the main roadway is being hung on to these suspenders, always working out from the towers to balance the load. Large derricks, called travelers, attach the steel members of the roadway and its stiffening trusses to the suspender ends. Here the derrick is handling one of the diagonal members of the stiffening truss, which forms the side of the roadway structure and helps keep it rigid. Bridgemen in the connecting gang ride the steel and guide it into place. Only after all these steel members have been attached is it possible to make sure that everything is in its right position. Will the cable sag to just that point shown on the original drawings? Have the suspenders been pre-stressed to just the right length? Let's not worry about it. The bridgemen aren't. They're as confident that everything will set properly in place as they are with their own agility. Like the trapeze artists in the circus, these bridgemen get paid for it. But unlike the trapeze artists, the bridgemen don't charge the spectator and don't holler alley-oop. Now the heavy floor beam over which the roadway will run is swung into place and connected up. These beams are spaced 25 feet apart across the span. The beams are 90 feet long and 8.5 feet deep. When the traveler has placed truss and roadway steel as far as it can reach, it moves ahead and repeats the operation. In this manner, the Bethlehem Steel Company erected their steel for this roadway in record time. Almost 1.5 miles of it hung from the Roebling cables. The truss and roadway members, such as this floor beam, were received at the base of the tower on barges. From these, they were raised to the roadway level and moved out to the traveler on a temporary construction railroad. As quickly as the steel for the roadway is placed, wood forms for the 6-lane concrete roadway are installed. As steel sections which will strengthen the concrete are placed over the forms, then welded, a continuous supply of cement is moved out in train loads. Small hand dump cars are quickly filled and just as quickly dumped. Settling the concrete preliminary to the final leveling operation guarantees a firm roadway for the heavy traffic it will carry. This leveling machine makes a smooth, sure surface. A final wetting and the concrete roadway is complete. With the familiar white traffic markers. With most of the dead weight in place, it is time to start wrapping the cable. By means of this machine, a continuous winding of wire is placed around the cable between castings. This makes the cable completely waterproof. The wrapping wire is wound on 2 bobbins which envelop the cable. As the machine turns, a wire is drawn from each of these bobbins through a fair lead to its position on the cable. Small steel fingers crowd the wires into close contact with those already placed. Ahead of the machine, the bridgemen remove the flat wire bands. Wrapping wire is spliced by means of a butt weld. Thus, the cable is entirely sealed against the elements. The wrapping is broken only at the cable bands where it nests in under a 1-inch groove provided in the casting. This groove is then caulked to make the seal complete. After painting, the cable looks like a large iron pipe. The footbridge is no longer needed. Section by section, it is slid down toward the center. Here, each section is lowered and trucked away. While the completed cable is being cleared, the suspenders are painted. Each man lowers himself to his work point and paints himself down. He takes his lunch with him and stays on the job all day. What a picnic. As the spinning of the big cables proceeds rapidly, several other operations are necessary. Strands are wrapped at intervals to hold the 452 wires in place. Let's move up to a tower top with the help of this tow rope and see what else is happening up there. When a strand is completely wrapped, it must be lifted from its temporary position at the tower top to its final resting place in the large saddles. As the strand is hoisted by hydraulic jacks, its entire weight of 250,000 pounds is transferred to a lifting beam through Roebling flat wire bands and Roebling grommets. These bands are to remain in the cable saddle, so their thickness is restricted to 5/100ths of an inch. On this account, and because only a limited number of bands could be placed along the beam, and because the results of a failure of this wire would be so disastrous, one of the strongest flat wires of the many made by Roebling had to be selected for this purpose. Meanwhile, each strand is further adjusted at the anchorage. Here, the strand shoe is being jacked back to bring the strand to the correct tension. When in perfect adjustment, a solid steel pin is inserted to hold it fast. We all remember from our school books the physical law that heat makes steel expand and cold makes it contract. On a main cable 7,700 feet long, that may make the newly completed strand, just fully heated by the sun, several feet longer than the strands buried down in the interior of the partially completed cable away from the sun's rays. This physical law made strand adjustment uncertain until Roebling spread apart the vertical rows of strands in the cable to allow a circulation of air through the cable to help equalize temperatures. Never used on any bridge before, this new Roebling technique is an improvement in the interests of safety and accuracy. Until 27,572 wires have been spun to form each main cable, will the bridgemen hurry to the task. Finally, the last wire is to make the last trip. Befitting this great occasion, the carriage will be covered with flags. To some bridgeman, it is a lucky day, for the one who has guessed the closest to the time the carriage comes to the anchorage wins a pool. Let's listen in.
Here comes that wheel, fellas, and I'm gonna win that pool.
You'll never make it in 20 seconds.
Come on, boy. Come on. Wow, Ted got it. Ted's under the wire. It's Ted. Come on, pay off, men. Pay me.
And so on May 20th, 1936, 191 days after the first wires were strung, the spinning of the world's longest and greatest cables was finished in record time. Thanks to the planning and direction of these Roebling engineers and to the skill and loyalty of the bridgemen. After the last strand has been set in place and all erection equipment removed, we see the cable anchorage in its completed condition. This cross-section shows how firmly embedded in concrete and fully protected the cable ends are. Over the saddles, the completed cable will always retain the hexagon shape. In the spans, however, it must now be squeezed or compacted into a circular shape. After being compacted by this machine, the cable will be 36 inches in diameter, 3 inches smaller than the horizontal width of the hexagon made up of strands. If Bill would move over, we could see the compactor. The compacting machine consists of a heavy steel ring containing 12 radial hydraulic jacks, which squeeze the cable with a total force of 720 tons. One of the many Roebling flat wires is easily clamped around the cable to hold the cable wires in a circular shape or section after the compactor has moved on. Using a high-grade flat wire prevents the cable from springing back to its original shape after the tremendous pressure of the compacting jacks is released. With a template and scale, an engineer checks the final diameter of the cable. With the cable compacted, the next job is to place the cable bands on the cable. These are the castings which carry the hangers or suspenders. At the bottom end of these suspenders, the roadway of the bridge will hang. Cable band castings are made in two halves, which are clamped together tightly by means of bolts, and the friction thus developed prevents the bands from sliding downhill. The nuts are first taken up by a large wheel wrench turned by a drive rope around its rim.
25 years ago, the great Golden Gate Bridge was just taking shape. Completion was many months away, but the country watched with fascination as the spinning of the mighty cables proceeded hundreds of feet above San Francisco Bay. One of the nation's most ambitious engineering projects of its day, the majesty of the Golden Gate Bridge was apparent even before the great span was complete. "25 years ago, Jack Dempsey got a champion present, a 1,000-pound prize-winning steer. Jack was a restaurateur, then not a fighter anymore, and the steer went from champ to chop.